Hello guys. The question we see today is strictly related to the discussion in the Moodle about the sections inside the ramjet engine, what happens in which section, what kind of model to use, and actually how to calculate. Right. To make it, we have to split our task in two different models. I will show the picture I've made. It's in Autodesk Fusion. Very similar picture to what we have in the work one, explained after the diffuser. So we have the inlet section here that flow comes after the diffuser. I chose some arbitrary value of Mach number, but you take the Mach number you receive after calculation of the diffuser, after optimization of your diffuser. And then flow goes to expand from smaller section. Here I have 30 millimeters, for example, and then the complete expansion is to 200 millimeters. Okay, so section 4 is expansion. This expansion we can calculate by already known area-Mach number relation. One example I can show you today, and I hope it's not very difficult. Then after flow expands, subsonic flow, right, expands. It remains subsonic, it never can be supersonic anymore in this closed volume. Then we have a constant cross-section, volume 5, where we have heat addition. Since you did not study, or many of you did not study yet the theory of combustion, I simplified heat addition by some temperature rise. Right? This temperature rise, as I stated, I think it was 1000 Kelvin. Temperature difference that happens on this heat addition process. What happens when we add temperature to the flow of constant area? We have an expansion, right? The flow expands, its density decreases, and velocity increases. Theoretically, acceleration of the flow inside a constant area duct can happen until Mach 1. It cannot become supersonic. To accelerate the flow just with the heat addition to supersonic velocities is not possible. So to have the nozzle is the requirement to generate a thrust. So we can accelerate the flow only inside the nozzle. Heat addition only creates extra energy that can be forwarded to flow acceleration or change of the velocity to supersonic. To calculate this heat addition, you use a valuable book, Modern Compressible Flow with Historical Perspective. We have it in the library of the Anderson. If you do not have access to this book, today I will show you the equations that describe this heat addition, and easily you can use them to calculate change of temperature, change of the pressure, and change of the Mach number during this heat addition process. Okay. After we add heat, we recalculate the flow properties according to the theory explained in this book. We go to convergent divergent classical nozzle, which is quite perfectly explained by Anderson in Fundamentals of Aerodynamics. And this calculation is also very simple. I will show you the equation today to calculate this parameter. So first, let's go from the left side to the right side. And meanwhile, if you will have questions during my discussion, you can always interrupt me and ask these questions, because I cannot see chat while I'm sharing this screen with you. Transition from region 3 to region 4. I remind you, it's the area-Mach number relation that helps us to solve this problem. And the area-Mach number relation is given in the Anderson book right here, equation 1032. It relates area in any arbitrary section area of the throat where Mach number is equal to 1 and Mach number at this same section as the area. So M and A are happening in the same cross section. Probably you already know the advantages and disadvantages of such approach. Is the formula very simple, allowing to calculate as Mach number in any cross section, but this Mach number we receive would be constant for the cross section, so it does not give us the variation of velocity in this cross section. It just gives us the average value of Mach number, so we cannot see any type of boundary layer, we cannot see the flow circulation, we cannot know if the flow separation happens. So very averaged, quasi one-dimensional flow model allows us to calculate average flow parameters in each cross-section. So area-Mach number relation can be applied cross-section by cross-section. You cannot see other things than the average values. So this problem here is the following, that in the very initial part of the flow where is Mach number is 0.75, for example, or any subsonic Mach number that you calculate, expanding to region 4, we do not have a throat. So we cannot use our area Mach number relation simply because A asterisk is not known. Our first goal is to calculate this A asterisk. How we can do it? We use the area Mach number relation. Okay. Instead of area, we submit our area which we know, for example, area 3, right, in the section 3. And instead of Mach number, we submit Mach number 3, or Mach number at the exit of the diffuser. After we calculated the diffuser, we know the Mach number, and also solving geometrically task, right, the first part of the work, we know the area, which is the area of the exit of the flow. We submit these two values into the area Mach number relation, and we receive A asterisk. This A asterisk will characterize to us the possible throat. So if in one moment our flow that is subsonic, exit of the diffuser, will constrain, okay, then Mach number 1 would appear. So this area asterisk is giving to us the value of this this area. But we do not have this in our real structure. This A asterisk is just needed to calculate the flow, right? So it's kind of a geometry that does not exist in our real diffuser because diffuser does not constrain the flow anymore. It's just used as a constant for our further calculations. So now if we look to area Mach number relation, we see A divided by A asterisk in square is equal to a function of Mach number, this function 1032 that you can see on the left side of my screen, has only two unknown. Now A asterisk we already calculated by the previous step, and we have unknown area and Mach number. So what we do, we just take any area we would like to know the Mach number. For example, the exit area, this big one, where the area is actually equal to 200, and we use this area as A. So our area would be 200, for example, and my A asterisk I already calculated from the previous step is I also involve in this equation, and applying these parameters to area Mach number relation, we calculate which is Mach number. In this case, it will be M4, I think, right? M4 at the exit, at the end of the expansion. At the end of the expansion. If we would like to calculate the Mach number somewhere in the middle, anywhere, we just need to know which is this area of the cross section. In the section we are interested to calculate Mach number. We take this area, we take the A asterisk previously calculated, and using area-Mach number relation with only one unknown, we calculate this Mach number at our cross-section I that we are interested to know. So that's the way. Okay, I would like to first to explain you the theory, and then I will show you example of calculation. Okay, so we know M4 at the exit, right? Where the area is 200, use this A asterisk, I know M4. With known value of M4, and assuming that flow is still isentropic, I know how to calculate the flow properties, right? I can calculate P04, I can calculate T04, and the density as well as a consequence of the equation of state. I hope it's clear because the calculation of isentropic flow properties for any Mach number I gave in the examples, if you would be interested in future, I will give you the link where these formulas were used and how exactly was calculated the temperature and pressure, stagnation properties and static properties. Okay, so this, I hope parameters of stagnation pressure, stagnation temperature are not a problem. We use parameters at the exit, right? At the exit of the diffuser, these parameters are same. Knowing these parameters that are constant for the isentropic flow, P04 and T04 are same as P0 and T0 from the diffuser exit. And from here, we use formulas to calculate T4 and P4 by isentropic relations. These isentropic relations are in the Anderson book. We have discussed them, I think, already some time ago. If not, I give you the link to the video if someone will not find isentropic relations for thermodynamic properties. Okay, we know temperature, we know pressure, we know Mach number at section 4. Okay, easily. Using isentropic relations, these thermodynamic properties are calculated. And then we add some heat. I unfortunately don't have now that book I cited. Is another book from Anderson. And but I have written the equations, so probably I will just write for you. I will also leave this video later, and you will be able to take formulas from the video, or you can annotate right now with me these formulas and you can use them for your calculations if it's very urgent. If you have access to the book of modern compressible flow of Anderson, just take from the book, it's the same equations. Okay, so the first equation is actually opens to us the way to increase the temperature, because when we are releasing the chemical energy, we add this energy to the stagnation property, to the stagnation temperature. So the stagnation temperature at two different sections, okay, I will write between section 5 and section 4, T05 divided by T04. So it's the ratio between the stagnation temperature, and this ratio is known because when you calculate T04 after the diffuser, it stays the same, right? And T05, I will write down here. Oh, it's not visible anymore. T05 would be T04 plus delta T. This delta T is the heat addition temperature that I wrote in the task of work 1. I think it's 1000 Kelvin. So T05 is 1000 Kelvin more than the T04. That's simple. So you always have the ratio of stagnation temperatures. And then according to the theory, this temperature ratio, stagnation temperature ratio, would be function of Mach number at region 4 and region 5. It will be the following. It will be a product of three groups. The first group is 1 plus gamma m1 in square, m1, m4 in square, divided by 1 plus gamma m5 in square. Okay. The second group would be m5 divided by m4 in square. And the third one would be 1 plus gamma minus 1 divided by 2 m5 in square divided by 1 plus gamma minus 1 divided by 2 m4 in square. In this equation, we know the left side, T05 by T04, right? As I just explained you, we know M4 by previously calculated value, as a previously calculated value, and the only unknown here is M5. So from this equation, we receive which is the value of Mach number after heat addition happened. We do not see the process of the heat addition by itself. We do not know how long it takes because it's not inside the equation system. We do not see other perturbations, for example, turbulence, right? The vortex evolution, etc., because vortexes and other flow aspects, they are outside of this model, definitely, right? And so we do not know how long is this process. We know that for the real ramjet, this heat addition process takes, if there is no additional device that helps, around 10 diameters. So this heat addition is quite long, right? 10 diameters of the motor. But if we have the additional devices like turbulizers and flame holders, this distance could be much shorter, could be around 2 or 3 diameters, depending on the design. But now design is not the question. Just I tell you that inside the region 5, we do not determine beginning of the process and evolution of the process, right? We see only the entrance as parameters after the section 4 and the exit parameters are at the end of section 5. We do not see the evolution. When we have Mach 5 calculated using this equation, we calculate real temperature, static temperature, and the static pressure. These formulas are given. I think there is no big need to write these formulas. I will just use the stagnation temperature part, and I will mark for you that just a moment. It will be this part here is the temperature 5 divided by temperature 4. Okay, these first two groups of the equation of stagnation temperature ratio. And the static pressure is just the first one, this one, just this. Yeah, there is one error. There is a square here. Okay, and there is a P5 divided by P4. So only this first group is pressure ratio, product of two, first and second is the temperature ratio. So when we know M4 and M5, we can calculate the right part of the equation for temperature pressure ratio, and knowing temperature 4 and pressure 4, we can calculate temperature 5 and pressure 5. This is how things go. Depend on the Mach number, these parameters they may change, right? But definitely we know that since flow is accelerating here because of the heat addition, Mach number increases, so pressure 5 would be a bit smaller than pressure 4, can be more or less, depend on the value of Mach number, depend on the acceleration level. And we know that temperature 5 will be bigger than temperature 4 because of the stagnation temperature addition. Okay, and the temperature 5 would be somehow close to temperature 0.5. So this is it. This is it. We obtain after calculation using this model parameters of pressure 5, pressure after heat addition, temperature after heat addition, and of course Mach number after the heat addition we also have. Then we go to the third section of the motor. We calculate convergent divergent flow. According to known methodology, same area-Mach number relation as we had on the first part of our calculation. We use the same equations to calculate the last part of our system. Here, there is a following aspect that since we changed the temperature and we changed the Mach number, flow is not isentropic. So we have a different value of throat here in the first section and here in the last section. So we needed to use area-Mach number relation again to calculate this throat one more time. How to do it? We have the area here at the exit of heat addition, also this 200. I think it's 200. A is 200, right? And we have a Mach number 5, Mach 5 known. After calculation of heat addition, we know. So using this area and the Mach inside the area-Mach number relation, we write that A by A asterisk in square is a function of M. This is 5, 5. From here, we calculate A asterisk, the new one, the new value of A asterisk. And now it will be a real throat that we have in our motor. It's shown here. I already did some calculation. I will show you now very fast how I did this calculation. And I think it's quite simple because there are many videos about the topic of using of area-Mach number relation in the internet, including my examples, which I did a lot in the previous semester. They are inside the list of examples of the nozzle calculation. I think it will be not very hard to use this theory. So this is the theoretical background of our calculation. As you may see, this calculation is nothing of very hard from the computational point of view. I would like to show you now the example. Okay, this is the program. Don't worry about the language because it's a specific language of Mathematica. It's more intuitive than other languages. It allows to do transformations, etc. So here first I define the area-Mach number relation as it's stated in the book. Area by throat ratio as a function of Mach number from the book. Right here it's written. Then I use my area Mach number relation to calculate throat. To make it, I set as area my 30, defined as geometry, right? As gamma, I've set 1.4. I don't like to use in this program Greek letters. It's also possible to write gamma in Greek letters, but I use just G because I can type from the keyboard easily. There are also shortcuts for Greek letters to type fast, but I don't like to remember them, so I use just G. So it's gamma. And my exit Mach number. I know that in MATLAB you are probably using the syntax is a bit different, but the idea is absolutely the same. I use method of Newton to calculate this root of the area-Mach number relation with the known list of parameters that I just set, and I calculate which is the throat, starting my method of Newton from value 25. 25 is initial parameter from where we start calculation using method of Newton. I hope you still remember numerical methods subject. And I obtained my throat. So my throat was 28.2375 millimeters. This throat I do not have, as I told you, in my design. Is just used as a parameter. Sorry. Just used as the parameter to calculate other geometrical, flow behavior according to my geometry of the motor. And then I calculate the Mach 4 after the expansion happens. So what I do, I use again the area-Mach number relation, right? I use already found throat from the previous calculation. I know the syntax is looking strange, but it's nothing of very complicated. If you like, you can study Mathematica in a few days easily. And I use gamma 1.4, and I use the area value of 200, so it's complete area when the expansion finished. And I received that is Mach number 4 is 0082. Something similar to what we have in the real ramjet motor. When expansion finishes, the flow enters to the combustion chamber with a very small value of Mach number to have efficient combustion process. But it's another discussion of or probably of another course. If you like a lot this kind of theory, you can go to see next subjects, which are aerospace propulsion and aeronautic propulsion, where you can see all these calculations, how they are made with Professor Domenico. So this at this point, my calculation finished. I obtain Mach number at region 4, and then I set up my equations of stagnation temperature ratio, static temperature ratio, and static pressure ratio from the book of Anderson. I set them as 0.2 by 0.1, so this is why I mistake a bit during my written part, because it's given in the book as section 2 and section 1. Usually we use section 2 as exit from the control volume and section 1 as entrance to the control volume. So this is why I use the same methodology in my calculation here. But it's absolutely not a problem, right? We just change the index and we use the same formula. Absolutely same equations that we have in the book. And then to calculate by that those equations, I use my list of parameters is for Mach number before the heat addition, I use Mach 4. For the stagnation temperature, I use 1500 Kelvin, and for at the exit. At the entrance, I use 500. So the difference delta T is 1000 as we have in our work one. I assume that I already know my T01. I did not calculate the diffuser before. So I assume that by calculation of my diffuser, I already obtained T01 500. But in your case, of course, will be a bit different value, but the method is the same. And gamma is 1.4, adiabatic constant, adiabatic coefficient of air. And I use the equation for temperature T0 ratio, right? And I find which is the Mach number at the exit of my control volume, also using the method of Newton with the initial guess of Mach number 0.5 as a solution. And then I use this solution. This percent means that I used previous solution, previous result. For example, I receive M6 and then I use this M6 in the next calculations. And double percent means that I use 2 times previous result. Right? Here with the list of my parameters where I'm using the same value of input Mach number, input stagnation temperature, output stagnation temperature, and same gamma for all equations. And then here I receive that my Mach number after heat addition changed. Now it's 0.144,685. And before it was almost 2 times smaller, right? So because of heat addition from 500 to 1500 Kelvin, my Mach number changed, right? And take a look that here we must receive always subsonic Mach number. If you start receiving something of supersonic, probably you have an error inside the method of Newton or some other error inside the equation. So acceleration due to heat addition can be made only for subsonic flow. Maximum Mach 1 happens, and then flow naturally reduces the flow velocity, because in the real flow we have a boundary layer that grows, we have losses, we have heat exchange with the wall. So naturally this Mach number will never be supersonic, it will be always subsonic. And with growing losses along the pipe, the flow velocity actually will become smaller and smaller and smaller. But okay, it's not the case. So we receive rise of Mach number on heat addition. And using this M1 and Mach after heat addition, Mach before heat addition inside the ratio of thermodynamic properties, I obtain ratio that shows that temperature 2 by temperature 1 is almost 3 times. And it's very, very similar to ratio of stagnation temperature. As you see, it's exactly 3 times here, right? And almost 3 times in this case. It's not exactly 3 times. It will be always smaller, these values, than the ratio of stagnation temperatures, because we are accelerating. And because of acceleration, we lose some part of temperature to velocity. So the potential part of energy goes to kinetic. And we have a decrease of stagnation pressure because of acceleration, as you know, by starting from the equation of Bernoulli, right? And finishing by equations of the compressible flow. Behavior of pressure on accelerating flow is this, that it's decreasing when flow is accelerating and pressure is increasing when the flow is decelerating. Okay, that's it here. And then by the same method, I calculate the throat using Area-Mach number relation. I use equation of Area-Mach number relation with the known area gamma of gas constant, adiabatic constant. And as a Mach number, I use my Mach number received after the heat addition. So it's this list of parameters: area of 200, gas constant, adiabatic constant 1.4, Mach number is equal to Mach 5. Going here is parameters right here. So using Area-Mach number relation from this equation, I obtain which is the throat. And according to this calculation right here, I obtained that my throat is 49.38 millimeters for this particular calculation. It means that if I decrease the area to this value, that my flow will accelerate, right, from Mach 0, 144 in 200 millimeter section to Mach 1 exactly in 49.3 millimeter section. And then after I accelerate to Mach 1, I can have acceleration, further acceleration to the supersonic flow. So using this throat, I can calculate flow properties, Mach number, temperature, and pressure in any arbitrary cross-section I would like to know in a supersonic and also inside the subsonic section of this nozzle. Such calculation I will not repeat right here because I already showed it. I just will give you the link where this was shown. You also can find by yourself going to that PDF which I share in Aprender and search of nozzle calculation or examples of nozzle calculation or examples of isentropic flow calculation. All these simple things are there. Okay, that's it. That's the theory. That's the calculation example I showed you. I would like to know now if you have another questions, if it was clear, if something was not really clear, and I am open to hear your questions. Ok.
Oi, professor, o Arthur aqui. Eu tenho uma dúvida, mas não é sobre isso não. Eu vou começar essa parte hoje ainda. É mais na parte 1, professor, do trabalho, em que a gente tem os valores de D interno e D. Eu tô com dúvida. Esses valores, eu vi aqui no seu desenho que você já colocou como 200. Eu posso repetir esses valores? Porque eu não consegui achar eles.
The geometrical source means that when you optimize the diffuser, you already know theta 1, theta 2. Plotting these angles, you will find this intersection of shock waves right here. And then you will know where this intersection of shock waves will start generating normal shock waves. So this point of normal shock wave touching the surface will be known. Let me make a bit bigger so it will be better. So this point will be known right here. Position, geometrical position of this point. And then what we do, we have to extend this line by tangential curve, by tangential radial curve, right? Some
Sim.
arc, let's say some arc of some radius similar to some big value, right? Similar to the diameter, something like this, or more than diameter. So we can obtain this internal diameter. We can obtain this internal diameter. It will be a bit bigger than this point here because of this curvature. And this arc here is making our flow horizontal again. Okay, so the purpose of all this duct subsonic part is to rotate the flow to horizontal direction. Okay, so this flow becomes horizontal. This radius, unfortunately, there is no analytical formula to give. You can just imagine or just take some value that will look nice. This actually curvature and this curvature here, they start from the same angle, but they have different radius. They have different size, right? And this you will find only numerically when you simulate in ANSYS Fluent. You will see many different options. I think I already have a video about this, or several times discussed about this, about simulation and search of these curvature, and then you will know. Then you will
Decisões.
know,
Tudo bem.
yes.
Uhum.
But now for analytical calculation,
Não, mas já ajudou
D is
bastante.
200, right? D is 200. And the internal you obtain when you finish this geometrical problem. When you build all according to these angles here, you will see how much would be this D internal.
Uhum.
You will have it just by drawing.
Tá.
This problem of diffuser optimization is dimensionless. It does not depend on the value of D, because any linear dimension does not enter into the problem, into the model to calculate optimal angles. So angles, they do not depend on the diameter. They are same for any size of the
Eu achei
diffuser.
isso
For
interessante.
similar diffusers, beta and theta will be same. Okay, so you can zoom to big structure, you can shrink to a small structure. Beta and theta will not change if the diffuser is similar. You know what is similar, all right? We have in aerodynamics definition of similarity. So all the geometry angles are same. I mean, they can be zoomed in all dimensions, all directions equally. Okay, so this is the diameter. The int you find by drawing your diffuser approximately. It's not important if you do a mistake or not, because since flow inside region 3 is isentropic, stagnation temperature and stagnation pressure will remain absolutely same. And for you, it means that when you will expand again inside the combustion chamber, you will reach the same value of temperature and pressure independently on your the int value. If it was small or it was too big, it's absolutely not important. You will have the same value of temperature and pressure as they should be. Is independent parameter. Actually, the int is some parameter that for you is absolutely not important right now. You guess some value, you choose some value that you like, right? More or less what you obtain, and you make calculations. In your calculation, you will see that it will disappear with the calculations which I just showed you. Okay.
Perfeito. Obrigado, pessoal.
Book I suggested last time, you will see that this is called optimal diffuser. When the three shock waves meet at the point of the, let's say, the leading edge of the body or the leading edge of the missile or the engine. Okay, this is the optimal. There are other possibilities. We are looking on the optimal operation of the diffuser. We are not looking on other different flow pictures when the, for example, Mach number infinite is bigger than the shock waves they go inside the diffuser. Okay, when the Mach number is too small, then shock waves are outside of the diffuser, creating some the attached shock waves, etc. So it's simplification for you, and we see only this optimal case. Okay.
All right. I was going to exactly ask about the geometry of the drawing of the inlet of the
Yeah,
diffuser, but
somewhere in
now
the
this
video I actually
makes
explain
sense.
how to build this profile of external wall and how to build this profile of subsonic part. I think we could find actually also many things that I've explained last semester, previous semester. I did not record because failed my recording, my video corrupted. One time we had no energy, and so I could not restore my video. So it was a problem. But I'm ready to explain one more time. There is absolutely no problem. Please let me know if there are more questions. I am waiting to answer your questions.
Professor, só mais uma coisinha, acho que ainda sobre isso aí. Desculpa ficar perturbando. Mas, assim, para fazer o desenho dessa estrutura no CAD, eu iria abrir no CAD ela para facilitar as coisas, né? Eu primeiro criaria o θ1, uma superfície com θ1. E qual que seria o tamanho dessa
size,
primeira
because
estrutura?
sizing you put later. You don't know the size, the initial size. Actually, if you read carefully the book, you will guess. There is an explanation, right? But if you don't know,
eu vou dar uma olhada melhor nisso, então.
Do not have to worry about the size. You just plot θ1, beta1. Then at some arbitrary point, you start making θ2, beta2. You will see where they will start to intersect. They will meet in one point.
Okay.
And from that point, you will start making the normal shock wave. It will be perpendicular to this line. Okay, these two lines will be perpendicular, and with these three shock waves, you will absolutely completely close the equation of the geometry. And then just extend the subsonic part as you think, as you expect. The most important in this subsonic part that this area here would be a bit bigger than this area here. So this area is a bit smaller than this area here. Otherwise, your flow will start to expand again and will start to accelerate to supersonic velocity again. And this is not what we want. We must constrain the flow. We must decrease, but decrease it quite gently, you know. If you decrease the velocity very fast, you will have very strong back pressure, so your flow will basically stop and will start to go in opposite direction inside simulation. So this change should be very smooth of the area, should be smooth, right? Should be slow. How slow, you will know only inside numerical simulation. Another comment I would like to do for you is the geometry of the nozzle, which was asked also by Alexis, that Area-Mach number relation does not see the shape. It does not allow you to obtain shape. It just allows to calculate average values according to the area. So when the area is same, for example, inlet for both nozzles is same, throat for both nozzles is same, exit. It means that all flow parameters will be same in these cross sections. Okay, so the model is not perfect. The model is giving to us average parameters. It does not tell us which should be the shape of the nozzle part. Shaping of the nozzle is another chapter that you can study, and actually is included inside gas dynamics. Shaping of the supersonic flow, and the supersonic nozzle has to go according to the method of characteristics. Method of characteristics is relatively simple for planar flows, as we have here, but more complicated for axis-symmetric flows, but also not so much difficult, actually. If you would like to study a lot, it's just solution of ordinary differential equations that simple, right, with any method, like method of Runge-Kutta, for example, or under any other method could be solved. So it's not a problem, but area-Mach number relation cannot give you the shape. Area-Mach number relation gives only the Mach number on specific area. That's it. And shape is method of characteristics. Subsonic part of the nozzle can be designed only by a test. There are many works published in this area, design of subsonic and supersonic nozzles. If you go to search in databases of articles, publications, all this was studied many decades ago. And even nowadays, there are modern research, which study in details shaping or profiling of the nozzle. But this is unfortunately is not the goal of our subject here. We just see the superficial things, right? If you would like to know more, you need to study other subjects, as I told you, aeronautic propulsion, aerospace propulsion, or to make TCC or PBIC with me, and then you will know much more about these topics. If you like, okay? It's not obligatory. Please ask other questions if you have.
Good afternoon. I have several things to say. First, the diffuser, the diameter of the diffuser is given in the initial data for Arthur.
Let me see, where is it?
So it's 0.1 meter.
Right.
Just before the table with our names.
0.1 meter. Yeah, before, for previous students some time ago, I gave 0.2 meters. Now I give 0.1. It's absolutely not important. Not important. It just gives you the dimensional parameters, like you can calculate the drag, for example, or you can calculate the thrust using the diameter. There is no other purpose to know the diameter because we see dimensionless picture. Mach number does not depend on size.
And now here is my question. If we don't know the shape of the nozzles, how can we have differences in the calculations for question 5? Do we have to take an arbitrary section and to see
these two nozzles, right? So I actually showed here.
Yes. The question 5, if we have to calculate things, if we don't know
what
shape,
is the answer?
There's no difference to have.
So there are two nozzles, bell-shaped conical nozzles, and they are continuous nozzles. Even here inside the throat for conical nozzle, you can use a tabular values of the area, and you can make many discrete points to calculate the Mach number distribution. Same thing right here. You can or make single function, but I think it's not is not so important to make a single function. You can just make a list of points and put the area in these points, and of course the axial direction, axial distance, right? So you will have this as an input data. And then since two nozzles are different in the middle, here between inlet and throat, you will have different results. Same after the throat. Since there is a difference of shape, you will have different results in the middle of pressure, temperature, Mach number, density, right? All these parameters here, and the velocity also. So the flow properties will be same only in 3 points. They should be same only in these 3 points and will be different in all other points. What does it mean to us? You use two different data sets for the area, right? And then you join together the plots. For example, you put two plots on the same graphics for one nozzle and for the other nozzle. And you see if they are same on these 3 points, your calculation probably is correct. And don't forget, you must have M1 in the throat. If you see very different inlet, very different on the throat, and very different, or at least some difference. If you see at least some difference in any of these 3 points, it means that something is not correct. I saw many of such works that students do this mistake. They, because of some reason which I do not understand absolutely, they obtain same value of inlet, throat, and exit for both nozzles, and they obtain different flow parameters in these 3 points for both nozzles. It's physically impossible. By the model, it's not possible. And then many people present. I know that there are programs in MATLAB. There are people who are doing this not for free or for some, I don't know, friendship. And people make for other students. I know that it happens because I see many similar works. And if I see such a result, which I already expect, right, from the wrong code, because correct code could not deliver different data for same conditions of the flow for same areas. I know that this was produced by someone some time ago, and I give very, very low evaluation or reprove this kind of work. So be careful in this thing, and do not use programs that are created by your previous colleagues. It will absolutely not help you to pass this course. I will see, and it's better to write your own code. As I showed you today, it's very few lines, as I showed you today in my program, very few lines to calculate the point. And then you have calculation of 1 point, like I show you here, any point, and then you just make a loop. Instead of one area, you put a list of areas and you receive a list of answers. And that's it, your work is done. Look how simple this code is to calculate the distribution of Mach number. Same, very short code can be written for any other thermodynamic parameter, and you receive the answer. So it's, for my opinion, it's not difficult. But if you have problems, I'm always ready to discuss. I am ready to pay by my time explaining this, because it's my job to explain. And I want you to make this by yourself, not use other people programs. It's not nice. Okay, I hope I answered your question. It's more, let's say, it's more than you asked.
Yes. So if when we are going to do the drawing, we just draw an arbitrary diffuser which is looking good,
Yeah,
or we
when
take the
you
results
have
that we have for the
theta and
sections
beta,
from the
you must
previous
have the
question.
same parameters, right? Theta and beta should be followed. Subsonic part you draw as you like. The subsonic part, as I told you, flow here is isentropic, and not important how different it will be from the real diffuser, because it conserves the pressure and stagnation parameters. So it's not so much important, right? So you just use this beta and theta, they should correspond to your calculation, right? As for the nozzle geometry, these are only recommended. Somewhere I put here recommended sizes. It does not mean that you must use exactly the sizes as I draw you here. Maybe you find much better geometry, of course, because real nozzle bell shape, they are not so simple as shown here. It's not just one and 2, 3 arcs, right? It may be different. If you think that would be nice to calculate different geometry, you calculate different geometry. What is important, you use calculated throat. You calculate throat by the formula as I showed you. You have the inlet and exit equal. Somewhere is written that exit of the diffuser is the, or exit of the nozzle is equal to the maximum diffuser diameter. So you basically have a tube, right? And all the motor is inside the tube. It's not changing the diameter, not increasing in the nozzle part, right? And usually they do not decrease in the nozzle part because there is enough chemical energy to expand with the same diameter of the nozzle as you have the motor diameter. It's not a rule, but some simplification I propose you. I'm making some decisions for you because probably it will be simpler for now, and then when you know more other things, you make your own decisions in this design part.
I got a little confused at the start of the first explanation for the values used for the area. I was thinking the ramjet geometry would be cylindrical, and for the area I use the formula for the area of a ring, for example, in the section 3, and then I calculate the value. But when I was looking at the number found, I think we used the height as the area or something like that.
Planar supersonic diffuser. If you look to this word planar, it means that it's two-dimensional structure, is not axisymmetric, is not the rotational body. Okay, it's just plane, and the third dimension has infinite distance, basically. Two-dimensional, like we had airfoil, for example, two-dimensional structure. This one is also two-dimensional. This is made because theory of the shock wave, as you already studied, is planar theory, is not axisymmetric theory. For axisymmetrical bodies, there is another model, and it's not that simple as we have in the Anderson book. This model is basically outside of the discussion because geometry of the shock wave in the case of axisymmetric body is found solving the differential equation on every step. And for planar case, as you know, its solution of just algebraic equation is much more simpler. So this is why Anderson gives as an example calculation of planar diffuser, and I also go in this direction. So it's not the diameter, it's just the length. The area is the length, so D is the area by itself, right? You do not need to calculate circular area. It should be simpler. It should be much simpler for you. Just to change inside your MATLAB code calculation of the area, remove this PR in square divided by, or PR in square, and just leave it area equal D and finish. This is my suggestion for the nozzle calculation. It's for the nozzle calculation more important, right? There are also other possibilities, but they are not so nice that you start from a planar diffuser because you can calculate simply the geometry. You can, for example, you are calculating some diffuser of known thickness, let's say the third dimension, and then you transform this planar diffuser to a circular combustion chamber, and then you transform the circular combustion chamber to an axisymmetric nozzle, to rotational body. It's not so nice from the computational point of view, and it's not the case. So it's better to use a planar calculation of the area everywhere. So basically this diameter is the area by itself. Any diameter it's not the diameter actually, it's the size. It's the size.
Okay, now just out of curiosity, is there any advantage to use a cylindrical model for the ramjet, or would a planar a planar ramjet work just as well if you use this design? But
the advantage for you is now to study. This is the advantage. If you are talking about practical application of these diffusers, then we look from many different points of view. There are basically two. One is the cost of the product. When the cost of the product is lower, it means producing the same characteristics, it means it's better, right? So in this case, cylindrical pipes, they are always cheaper than you make some kind of rectangular body, right? And the other question is if this motor is making part of a flight vehicle that must be integrated inside the flight vehicle, then the diffuser will be semi-axisymmetrical, like just a section, right? Inlet device is just a section, or you can see in the some airplanes, the inlet devices as planar devices, right? In some missiles, you can see also planar devices, and they are making just a part of the diffuser. Usually, inlet devices on real structures, they are much more geometrically complex than just planar or just axis-symmetrical. There are always other parts of the equipment or other bodies that must be integrated together with the diffuser, and this is taken into account. But for the simplest case, if we are talking about the simplest application of such a diffuser inside the ramjet for the missile, for some air missile of another type of missiles, is just a tube, just axis symmetrical, right? Tube with the wings, with simple wings, and then it flies. Cost is more important than technological perfectness or integration, because just for the missile you do not integrate it anywhere. Just all the body is the missile, right? So you do not need to integrate it anywhere. So that's the answer. For the real application, we are looking to other things. Where is used this part? From the computational point of view, as I already told you, from study point of view, planar devices are much simpler because you just solve system of algebraic equations, and for axis-symmetrical you solve system of differential equations.
A minha também era mais curiosidade, igual o Aleph também, de que onde que aplicava esse tipo de motor, mas eu tô vendo aqui foguetes mesmo,
you
né, como
cannot
você
see this
citou.
type of motor.
Porque eu
This
nunca
type
vi
of
muito esse
this
tipo
type of
de
motor is
motor,
basically
assim.
for the war machines. How many wars Brazil has in the world? There are no wars, right? If you work in the military industry, you will see this in not in Brazil, because it's a much more advanced structure than just a solid rocket motor. For example, you need to organize process of cooling of the wall, process of efficient propulsion, etc. So there are many technical problems to be solved. Also, it's kind of technological secret, right, for many companies, and people will not just start publishing this because they are nice, right? Because it's giving the advantage to one side. If it gives an advantage, people will keep it not explained or in a secret, right? So it's a critical technology which is not so widely explained. But if you like, you can search and find some publications in this area from the Soviet Union, probably translated, much less from the United States, because United States, they protect more, much better the information. There are studies all over the world about these subjects, because nowadays there are ways to improve such kind of solutions, to make it more reliable because of new control capabilities, to make it lighter because of new materials, for example, composite materials. There are ways to improve. New fuels, new methods of simulation, where you can see any aspect of the flow inside this device. We can predict, you can plan how this will work and avoid some problems. So this is very interesting question from the practical point of view, right? But you cannot see it in real life because these devices are designed basically or mostly to kill people. So it's not so peaceful application. There are some peaceful applications we may see. For example, there are several projects of substituting higher stages of the rocket. When the rocket is accelerating to supersonic velocity, instead of just put on second stage liquid rocket engine, people can think to put this ramjet. It takes oxidizer from atmosphere and creates the thrust. There are many of such projects developed in the world by different countries. But there are no implementations until now because technologically it's very difficult, and I think that it's much more pragmatic to use technologies that are already in use than to develop something new. Look, just the SpaceX, which is, for my opinion, evolving in the story of aerospace propulsion. And all other countries, they are very, very pragmatic, very slow, right? And if not SpaceX, it would not be interesting to follow current development of aerospace. They are moving the edge because they are trying some new solutions. In all aerospace and military industry is not like this. People more conservative, much more conservative. They rely on already checked solutions, tested solutions, and that's it. This is why you cannot see. And not so many people would like to fly with supersonic velocity. It's dangerous, right? It's dangerous. It's quite dangerous. I think it was a very nice discussion today. I like a lot that we met for almost 1.5 hours. Could discuss things more than just a diffuser and the nozzle. Okay, if you have something else in future, please submit into Moodle. I check it every day, and then I will prepare and will present for you some things that are important, or to make work 1, work 2, or just to know about gas dynamics, because time is running, and this is the only chance for you to study with me. And it's very soon it will be finished. Have a nice week, and we meet next time when you need. Okay, goodbye.